Greetings, welcome to Electronic Circuits 1. I am Razavi and this is lecture number 24. Today we will continue to look at the common emitter stage and explore how we exactly bias the circuit for proper operation. So let's take a look at what we covered last time. First, we said that one flavor of the common emitter stage incorporates emitter degeneration, and that means that we place a resistor from the emitter to AC ground for operation of the device. And the motivation for using this resistor was that the overall gain of the circuit becomes less sensitive to process variations, to current variations and temperature variations and so on, as we can see by this equation where, for example, variations in the collector current are swamped by this constant value Re. And we also saw that in the special case, not very common, but the special case where we have this condition, the DC drop across Re is much greater than 26 millivolts, then the gain of the circuit is just the ratio of the collector resistor and the emitter resistor. So to the first order is actually independent of GM and the collector current and the signal level and everything else. So we also saw that the input impedance of the common emitter stage with degeneration is not just R pi, but is actually a R pi plus a boosted copy of Re. Re is boosted by an amount equal to beta plus 1. So the input impedance can be substantially higher than what we would have without degeneration. So degeneration has some interesting and useful properties. Now, one other degenerated circuit that we studied was just a simple current source, a bipolar transistor with degeneration in the emitter. And we saw that when we place the degeneration resistor here, and we bias up the device, and we look at these two terminals as a current source, what we observed was that the output impedance of the circuit has gone up. It used to be only RO, what we saw between collector and emitter, but as a result of this degeneration, the output impedance has gone up, meaning that we have produced a better current source with less variation as the voltage varies, and the output impedance was given by this equation. This equation tells us that the output impedance is not just RO, but it has this term which can be quite large. The way we memorize it is that it's 1 plus the intrinsic gain of the device, GMRO, times R pi in parallel with Re, that combination. So we will see as we learn more electronics that this equation plays a critical role in many types of circuits that we will see later. All right, let's move on. And today we'll go over a few examples of the degenerated current source just to become more familiar with it. And then we will turn towards biasing a common emitter stage with degeneration or without. So far we haven't really spent much time on that, and we would like to look at the practical issues in biasing. All right, so we will go over a few examples of degenerated current sources. So one example is this. Again, I remind you that if we have a bipolar transistor, properly biased of course, and we add some degeneration, then the output impedance of the current source is no longer just RO, but this overall expression. So here's a little circuit that I have cooked up for you. I have a degenerated common emitter stage or current source. So I have some sort of voltage here, Re, and then I deliberately add a resistor between the collector and emitter, and I call that R1. And now I would like to find the output impedance of this device. So if you remember, the output impedance is really measured between this point and this point, because the way we would do it is kill all the independent sources, then place this in a box, apply a voltage source between these two terminals and an AC voltage source, and measure the resulting current. But as an abbreviation, we usually just put an arrow and we say R out. And that's just a simple notation for what that would entail. Okay, so we want to find R out. How do we do that? Is this topology close, mappable to this topology or not? If not, we would have to start from scratch. We would have to kill the source, put this in a box, bring two wires out, apply Vx, measure Ix, and then see what we get. But maybe we can map this topology to this familiar topology. If you look at this very carefully, what we know from the small signal model of the transistor is that it has a resistor equal to RO from collector to emitter. So here we have a resistor called R1 from collector to emitter. So what we really have from collector to emitter in the small signal model consists of the RO of the transistor and this additional new resistor R1. And they are in parallel because they both go from the collector to emitter. So we don't really need to draw the small signal model of the circuit. But just to be sure, let's draw it quickly but not solve it. So here's the small signal model of the circuit. The independent source is set to 0. We have R pi and GMV pi. Then I have RO because I am not neglecting the early effect. Then we have RE. Then in parallel from collector to emitter we have another resistor R1. And now we're interested in this output impedance R out. So if I compare this small signal model with that of this topology, which we found last time, which we drew last time, I see that the only difference is a new resistor R1 in parallel with RO. That is the only difference. So perhaps what I could do is go back to the result that I already obtained, and wherever I see RO, I replace it with RO in parallel with R1, and I have the right answer. So I can just say R out is equal to 1 plus, so 1 plus beta. Okay, I think that I made a mistake here. Let me clear that up. All right, so this equation is actually incorrect. Let me write that correct equation correctly. 1 plus GMRO and RE in parallel with R pi. Okay, I'm sorry about that mistake. All right, so now we're going to apply that here. So we go back to our blue color. Okay, so we have 1 plus GMRO. Let's take RO and replace it with RO in parallel with R1. So 1 plus GMRO in parallel with R1. So that's this expression. But we go on with RE in parallel with R pi. And then the last term also goes from RO to RO in parallel with R1. So RO in parallel with R1. And that's it. We have found the output impedance of the circuit. So a critical point in analyzing electronic circuits is to be able to use our previous results and not have to draw the equivalent circuit again and write equations again, to the extent that we can. Not only does it save us time, it also gives us additional insight. Because if I just write the equations for this circuit and not realize that RO and R1 are in parallel, what do I get at the end? I get some big expression here that has RO times R1 divided by RO plus R1, etc. It's a big mess. But by recognizing these little features, we can readily write the result. Okay, let's look at another example. In this case, I have again a degenerated current source with a voltage of V0. And instead of resistor RE, I will use a constant ideal current source. So here's a constant ideal current source, I1. And I would like to find out how much this output impedance is. Okay, so now what do we do? Well, you go back to this equation and say, can we use this equation here? The only thing that has changed is RE. RE represented a finite resistance tied between the emitter and AC ground. And now we have replaced that resistor with an ideal current source. When we go to the small signal model, what happens to this constant ideal current source? Because it doesn't change with time, because its change with time is 0, it will replace by a 0 current source. And a 0 current source, a circuit that doesn't carry a current, is an open circuit. So I1 in the small signal model will be replaced by an open circuit. An open circuit has a resistance of infinity. So maybe what I can do is go back to this equation and replace RE with infinity. That will be the output impedance. Again, we don't need to draw the small signal model. So we say R out is equal to 1 plus GM RO times RE is infinite. Infinity in parallel with R pi just gives us R pi. So we have R pi, and then we have RO. All right. Now, if we multiply this out, we get R pi plus GM R pi RO plus RO. And sometimes we group these because GM R pi is just beta. So we can write this as beta plus 1 times RO plus R pi. And it is true that in most cases, beta times RO is much greater than R pi. So we can say roughly this is equal to beta RO. So that's a nice little equation to remember. If a bipolar device is degenerated by an ideal current source, then its output impedance is given by approximately beta RO. This is only this case, not in the general case. So that's a nice little equation that sometimes helps us. Okay, so one other note that I would like to make here is that the results that we obtained for the common emitter stage with degeneration in the previous lecture assumed that the early voltage was infinite. This voltage gain, this input impedance, and this output impedance were obtained under that condition. In this very special case, which is not the general amplifier, it's just one little circuit by itself, one little current source by itself, we assumed the early effect was not negligible. But for the voltage gain and the input impedance and the general output impedance, we did. So, can we find the voltage gain and the input impedance and the output impedance when the early voltage is not infinity? Yes, we can. But we usually leave these for more advanced courses. Especially the input impedance and the voltage gain are a little more complicated, and we don't prove them here. We don't derive them here. In fact, I usually don't remember the equations for the voltage gain and the input impedance if the early voltage is less than infinity. I would have to either derive it quickly, or I have to go back to my notes. That's why we don't usually teach them in undergraduate courses. But it's not a big deal. You can always sit down and derive them if you're interested. So from now on in this course, if we have an amplifier, a common emitter stage with degeneration, we automatically assume that the early voltage is infinite so that we don't have to worry about early effect. Is that a realistic assumption? In many cases, yes. But if in an engineering problem you realize it's not, you can always quickly sit down and derive the results. All right. We are now ready to look at some biasing techniques. So let's go back to a long time ago and see how we biased our common emitter stage anyway. So let's take a look at simple biasing. I hope you remember by now why we bias a transistor. We bias a transistor so that it has proper small signal properties, values, and operates in the proper region of operation. It has to be in the forward active region, so the base emitter has to be forward biased, the collector current has to be something reasonable, and the transconductance has to be reasonable, etc. So that when the signal comes in, the signal at the input can give us perhaps some reasonable change in the collector current, which we can use eventually to generate a voltage, a signal voltage at the output. Now, we said when we have a bipolar transistor like this, and we want to forward bias the base emitter junction, we put a battery here, and then we also had a battery here between the collector and the emitter. So this doesn't have any name, just call it V0. Sometimes this has a name, we call it VCC. Doesn't really matter. The idea was that this junction is forward biased by a reasonable amount, maybe 800 millivolts, and this junction is reverse biased, or at least has a zero bias across it. So this VCC has to be high enough. Okay. Of course, we have some resistors, etc. around. We're not showing those here. All right. So now, if we have a complex circuit consisting of several different stages, maybe some common emitter stages, do we connect a battery to every single one of those? That would be very cumbersome, right? We don't want to do that. So how do we create this voltage for this base emitter without a battery? You have to think about that. Well, we know something from basic circuit theory that helps us. We know that if we have a resistive divider, we can take a larger voltage and divide it to get a smaller voltage. Now, we do need one reasonable voltage, supply voltage, battery in the entire system, right? The system needs some sort of energy from outside to do amplification, etc. So we have one battery for this entire system consisting of many amplifiers. Let's say this is the battery. This battery feeds everything. It feeds the collector current, it feeds the other parts of the system. So the question is, can I generate the voltage that I need here from this battery? And if you remember that we have resistive dividers, yes, why not? So let's do it this way. We draw the transistor again. Here's our battery. And again, remember, the voltage difference between these two is VCC. So this wire and this wire have a voltage difference of VCC. It's like two terminals of a battery. I will take these two wires, go through a resistive divider, and produce a voltage for the base. So here's a resistive divider, and it connects to the base. So R1, R2, and that gives us some voltage. So for example, if VCC is 1.5 volts, and I need 0.8 volts, I can pick these two values to give me 0.8 volts from VCC. If I call this node X, I can say that Vx is equal to R2 over R2 plus R1 times VCC. Right? This resistor divided by the sum multiplied by this voltage, which is VCC. So that will give me the voltage that I need at the base. So I can just, if VCC is known, I can pick these values so that this whole thing is 0.8 volts, what we need for the base emitter voltage. That seems simple enough, right? So that's the way we do it. We don't need to have a battery for every base emitter. We just have some sort of resistive divider. Unfortunately, it's not as simple as it looks. We have to evolve with this and see what problems we face. But the principle is to eliminate the battery and replace it by some other more practical circuit. All right, so that's what we have, and it seems that it shouldn't be that hard to choose the values of these resistors if VCC is known, and I know that Vx should be about 0.8 volts. But a number of questions arise here, so I will write down the questions and I will try to answer them. So let me change the color of my pen to red, and so we have a bunch of questions here. Number one, what happens to the input impedance? Okay, this pen went crazy again. What happens to the input impedance? The input impedance of the basic common emitter stage, like so, was equal to R pi. That was the value that we measured between the base and the emitter in the small signal model. And that showed us how much loading this would impose on the previous stage, or how much attenuation this input impedance creates. We saw that if I have a microphone with a finite internal resistance, and we connect it between these 2 points, we will have some attenuation because this R pi is not very large. Now, what happens here? How much resistance do we see between these 2 points? Presumably, our signal will come to here and here, from somewhere, from a microphone or something. So how much is the input resistance that we see here now that we have added R1 and R2? Well, can we just look at it and predict what that is? Or do we have to draw the small signal model? Well, if I sit at this node, I remember that from this node to AC ground, I have R pi. That is R pi of this device. Are there any other resistors that go from here to AC ground? We have R2. How about R1? R1 also goes to AC ground because we know that in our AC model, we will set to 0 all constant values. This is a constant battery. Its voltage doesn't change with time. Because the change is 0, this point goes to 0 voltage. So it means that R1 is also going from this node to AC ground. So what we really have is the input resistance is equal to R pi, but in parallel with R1 and R2. So as a result of adding this biasing circuitry consisting of R1 and R2, we have inevitably reduced the input resistance of the circuit. It used to be R pi, now it's lower. So that's one issue that we have to face. Is the result acceptable? From this perspective, we want to choose R1 and R2 as large as possible. Preferably 10 times R pi, 20 times R pi, something much larger, so that we don't feel the existence of R1 and R2 after we add the biasing circuit. So ideally, preferably, R1 in parallel with R2 should be preferably much greater than R pi, so that the input impedance is still approximately equal to R pi. Now sometimes this is possible, sometimes not, but that is our preference. Okay, so that was the first question. We have to remember that. The second question is, how about the base current? In writing this equation, I actually tricked you, because if we sit here and just look at bias quantities, DC values, we have a current coming down R1 from the battery, but not all of the current through R1 ends up through R2. A small fraction goes to the base of this transistor. This transistor needs some base current. So if this equation is based on all the current of R1 flowing through R2. That's our good old voltage divider. But this is not the case, because we have some current flowing through the base. So this equation is actually not exact. This is an approximation. So let's go back and place an approximation here. So if we want to include the effect of the base current and find the accurate value of Vx, we cannot do it this way. We have to go through a little more mathematical labor. So let's do that. Let's do that and see how we would do this. Hopefully, in practice, we don't have to do that very often. But the idea is that you do it once in your lifetime so that you learn the procedure. And if at some point you have to do it, you're comfortable doing it. All right, so how do we do that? I know that there will be some base current this way. And let's assume that I know everything about the transistor. So for the transistor, I know it's beta, and I know it's IS. And again, as usual, we assume that the early voltage is infinite, so that the calculations are simple and reasonable. All right, so I need to solve that circuit. This is a biasing calculation. So in other words, we're really using the large signal model of the bipolar device, even though we don't have any signals. All right. Well, I will play a little trick here to simplify the calculation a little. And that's based on recognizing that this voltage comes from a battery, this battery here. So I can take this voltage source that goes to these 2 points, and this resistor, and construct a Thevenin equivalent for them. So here's what we have. We have a battery, VCC, and then 2 resistors, R1 and R2, and put this in a box and construct a Thevenin equivalent for it. And interestingly, it does not matter that this battery is serving different circuits. It's serving this circuit and this circuit, etc. No problem. You can always split this battery into multiple batteries in parallel and take one of them here and put it inside this box. Okay, it's a constant battery. We can do that. All right, so can we find the Thevenin equivalent of this circuit? Yes, Thevenin says the voltage, the Thevenin voltage, will be what we measure here before we connect it to the rest of the world. So that's, of course, what we know. So V Thevenin is equal to R2 over R1 plus R2 times VCC. And to find the Thevenin resistance, we set all independent sources to 0. This is set to 0, so it becomes a short circuit. And we find the resistance between these 2 terminals. This is easy enough, because if this battery is set to 0, we see that R1 and R2 appear in parallel. So the Thevenin resistance is simply R1 in parallel with R2. So now you begin to see why all of these little theorems that we learned in basic circuit theory are so important. You have to be comfortable with these, you have to be able to use them, you have to be able to recognize that a circuit lends itself to a Thevenin equivalent or a Norton equivalent or many other topologies that we have seen. Very well. So I can go ahead and simplify the circuit now. The circuit looks like this. We have a battery equal to V Thevenin. We have a resistance equal to R Thevenin. This is the Thevenin model of this part of the circuit with the battery included. And now this goes to the base emitter of this transistor. So base emitter of this transistor. And my objective is to find everything, find the collector current, the base emitter voltage, etc. Given that I know this value, I know this value, I know this value, and I know beta and IS. So how do we solve the circuit? Well, what we can say is that we have a certain base emitter voltage here, which we don't know yet, and a certain collector current here, which again we don't know yet, and then a base current here. So I can say that if I write a KVL in this loop, I say this voltage plus this voltage is equal to this voltage. So let's write it. We have V Thevenin, which we know is equal to this voltage from here to here. How much is that voltage? Well, we have a base current which we don't know yet times that resistance. That is the voltage drop. So IB times R Thevenin, and then plus this voltage, plus VBE. Do we know an equation for VBE in terms of the collector current? Yes, that's VT log of IC over IS. So VT log of IC over IS. How many unknowns do we have here? Well, IB is unknown and IC is unknown, but IC is just beta times IB. So I can write that like so. IB R Thevenin plus VT log of beta IB over IS. So this is a nonlinear equation, doesn't have a closed form solution, but no problem. If we have the values for all these things, it's not hard to calculate by iteration. We iterate and eventually we can find IB. Once we have IB, we have IC. Once we have IC, we have VBE, we're done. So that is the procedure for solving the circuit exactly. And that's fine. But in practice, actually, we don't go that route, primarily because we see that there is some sensitivity in the circuit to the beta of the bipolar device. If the beta of the bipolar device changes from 100 to 50 because of various effects, maybe from one sample to the next sample, maybe with temperature, etc. So if beta changes from 100 to 50 or from 100 to 200, then this current changes. If that current changes, this voltage changes. And that's not very good, because presumably this voltage is what this base emitter needs to carry a certain current. So we are hoping that this voltage is not sensitive to this current, which means we are hoping this voltage is not sensitive to the beta of the transistor. So how do we do that? If I want this voltage to be relatively insensitive to variations in this current. Well, if we choose the current that flows through this branch so large that even after we draw this current, this branch doesn't feel it, then this voltage is not very sensitive to IB. So we pretend that IB doesn't exist. We choose the current through this branch to be much greater than IB, maybe 10 times greater than IB, and then we connect them. So now IB flows, but it's a small fraction of this whole current, so the circuit doesn't feel it. Even if IB changes, the circuit doesn't feel it. So to reduce sensitivity of Vx, this Vx here, to IB and beta, choose VCC divided by R1 plus R2, which is this current here, before we connect the base, to be much greater than IB. Okay, so now if IB changes to some extent, Vx doesn't feel it. Vx is still approximately equal to this equation. So when I wrote this equation, my assumption, my implicit assumption was that this current is much larger than IB, and this approximation holds. And this is not just for mathematical convenience, but actually it's good for practical designs because we don't want to be sensitive to the beta of the transistors. All right, let's move on to the next question. So we asked two questions so far, the input impedance and then the effect of base current. And there is one more question that we have to address. So let's go and add a page here. Okay, the third question is the following. How do we interface this circuit with the preceding stage? So we have developed this biasing technique for the base of the device, like so. We have a voltage divider, R1, R2. This goes to VCC. And here's what we have. We have a battery here, we call VCC. And that feeds it here. We may have other stuff here. Don't worry about that for now. I'll just put some dots here. And this is what we have at the input. And we have created a Vx here by means of the two resistors, approximately equal to 0.8 volts. Everyone is happy. The transistor has its right base emitter voltage. The current through this is much larger than the base current. It's good. But now I have another circuit before this. Maybe another amplifier. And I need to connect them together. So here's another amplifier, maybe another common emitter stage, right? Like this. And the question is, how do we connect these 2 points? Can I just short them together? Well, yes, provided that before we short them together, the preceding stage is happy with a collector voltage of 0.8 volts. Meaning that this actually has been designed for a collector voltage of 0.8 volts. And this has been designed for an input voltage of 0.8 volts. And we can just connect them together. If we connect them together, then the two stages will work in harmony. There won't be any problems. We're good. So that's one approach. So we have two approaches to do this. One is design. Okay, my pen has problems again. Design preceding stage for V out approximately 0.8 volts and connect directly. And sometimes we call this DC coupling. call this DC coupling. All right, it's strange. DC stands for direct current. Direct current coupling is weird, but that's how we call it, DC coupling. All right, if we do that, then let's suppose that this stage is designed for a collector voltage of 0.8 volts. So when there's no signal, this voltage with respect to ground is 0.8 volts. And I come along and I want to connect this to the base of this transistor. Do I need R1 and R2? No, because that 0.8 volts that this base needs already is available from the first stage. So in that case, if we are doing DC coupling, we don't need R1 and R2 anymore. So the circuit simplifies to this. We have the previous stage here. It was designed to have 0.8 volts. And then we have the next stage. And we say, oh, this gives us 0.8 volts. Good. So we just connect them directly, and everyone is happy. So let's call this Q1, Q2, Q2, Q1. So that's one possibility. Very simple and very nice. All right. However, there are some cases where this stage would not be happy with 0.8 volts here for various reasons. It may need a higher voltage, it may need a lower voltage. So here's the problem. This stage needs 0.8, maybe provided by these. This stage cannot provide 0.8. Then how do we connect these 2 points? Well, we cannot connect them directly. We cannot have DC coupling. So we resort to AC coupling. So use AC coupling. And for that, we use a capacitor. So we have our first stage like so, Q2. And then the second stage has its biasing. So we have Q1, we have the resistors here, R1 and R2. This goes to a battery here, which is called VCC. Then there might be some stuff here. And then between these 2 points, because I need 0.8 and I have 0.8 by means of this divider, but this guy doesn't like 0.8, I have to use a capacitor between them. Now, if there's no signal, we have only DC quantities. So we have DC here, DC here. The capacitor is an open circuit for DC quantities. So this stage and this stage know nothing about each other. They have no interaction between their bias points, and they can be designed independently. When the signal comes in, the signal creates some voltage swing here. It has a non-zero frequency. So it goes through the capacitor, it goes through this, and so on, and it propagates. So for a signal, we can let the capacitor conduct. All right, so the question is, how do we choose this capacitor value? Let's call it C1. So we want C1 to be large, because if you remember from your basic circuit theory, the impedance of C1 is equal to 1 over C1 omega. Omega is 2 pi f, is the 2 pi times the frequency of interest. So we have to look at the lowest frequency that will be passing through this capacitor, the lowest frequency. For example, voice has components from 20 hertz to 20 kilohertz. So we have to ask, at 20 hertz, is this capacitor a good short circuit so that the signal goes all the way through? So we say C1 should be a reasonable short circuit at the lowest signal frequency. If it is a good short circuit at the lowest signal frequency, obviously it is also a good short circuit at the highest signal frequency. That's why we pick this as the worst case. Okay, so what do we mean by a reasonable short circuit? 1 ohm, 10 ohms, 100 ohms, 1 kilo ohm. What constitutes a reasonable short circuit? Well, it has to be in comparison to the environment in which the capacitor is used. This capacitor sees this resistor on this side, and then the input impedance of the circuit on this side. All right? So what we can do is, for example, we can choose this capacitor impedance to be much less than the input impedance of the circuit. So we choose 1 over C1 omega to be much less. We want it to be a short circuit, right? And short means this is a much lower impedance than the input impedance here. Why? Because then that allows us to minimize the attenuation of the signal from here to here. Right? This is a very small impedance. That's a very large impedance. We don't have much attenuation. So we pick this condition. This has to be much less than this input impedance, right? This Rin. And if you remember, we found just a few minutes ago that Rin is equal to R pi in parallel with R1 in parallel with R2. So after we are done with the design of this stage, we come along and choose this capacitor to satisfy this equation. And sometimes it's very difficult. This capacitor would be enormous, especially for voice signals. If you want this condition to hold at 20 hertz, you will see that this capacitor has to be very large. So it's not practical. Maybe you cannot do it this way. We have to do it some other way. But that's the procedure. Okay, so we answered the third question. And now we are ready to go and look at the design procedure for this biasing. So let me talk about this a little bit. Design. Okay, this pen is not very good. Design procedure for simple biasing. This is just a summary of what we have learned so far. We have a certain collector current in mind, right? We are given. Comes from power budget, comes from other things, but we know the collector current that we need, the bias current. That means that we know the base current of the device. We just divide by beta. If we know the base current of the device, then we want to choose the current through the resistive divider to be much higher, maybe 10 times. So we pick VCC, because this is VCC from here to here, divided by R1 plus R2 to be approximately 10 times IB. 10 times IB. That's one equation. What else do we know? Well, we want this voltage divider to give us approximately 0.8 volts. So we also know that R2 over R1 plus R2 times VCC is approximately 0.8 volts. So from these two equations, we can find R1 and R2. So now we have everything that we need. That's the simple procedure we would follow to choose the value of different components. Okay. All right, so the next issue that we need to deal with, and the reason I call this simple biasing to emphasize that it's simple but probably not very good, is the following. So let me change the color of my pen and talk about this new difficulty that we face. Problem of supply sensitivity. Okay, this, let me erase all of this, see if I can write it better. Sensitivity. So remember that we chose the current through these two resistors to be much higher than the base current to avoid sensitivity to the beta of the device. But there's another sensitivity that we have not resolved, and that is the sensitivity to VCC. So here's a simple example. Suppose VCC goes up by 5%. Why should that be? Well, when you connect a battery to a device, to a system, it has a certain voltage, and when the battery ages, its voltage goes down. Or if you have a voltage regulator that is used to supply a voltage to a circuit, that has some tolerance. Sometimes it's higher than specified, sometimes lower than specified. So we have to be able to run our circuit from somewhat higher, somewhat lower supply voltages. Okay, so VCC goes up by 5%. What happens to this base emitter voltage in the divider? Well, that goes up by 5%. If this goes up by 5%, this fraction goes up by 5%. So that means that VBE goes up by 5%. Okay. For example, if VBE is 800 millivolts, so if VBE is 800 millivolts, then 5% is equal to, let me write this more clearly. Then delta VBE is equal to 40 millivolts. So the base emitter voltage here, which is provided by this divider, goes up by 40 millivolts. What happens to the collector current? So IC goes up by exp of 40 millivolts divided by 26 millivolts. And how much is that? That amounts to 4.65. So I will write fold here so that you remember this is a multiplication factor. So the collector current goes up by a factor of 4.6, 4.7. That's huge, right? We can't tolerate that. So that's a problem. We designed the circuit, let's say, for a collector bias current of 1 milliamp, but when the supply went up by 5%, suddenly the collector current jumped to 4.65 milliamps. So that is a serious problem. And the question is, how do we fix that? Okay, well, to fix this problem, we actually go back to a familiar topology, namely the common emitter stage with degeneration. Degeneration not only helps with other sensitivities, it also helps with this sensitivity. So we'll go look at that. So CE stage with degeneration. So it's similar to before. We have a voltage divider here, except that we add emitter degeneration. So here's what the biasing looks like. So our supply voltage is here, VCC. We have a voltage divider, R1 and R2, and then we have an emitter resistor. I'm deliberately not drawing what goes here for now. We'll attend to that later. Okay, so this resistor impacts the sensitivity quite a bit, and it's very interesting to see how it does it. So we want to prove that if we have a degeneration resistor in the emitter, then the change in the bias current as a result of the change in the supply voltage is less than what we calculated before. For example, if the supply changes by 5%, and this voltage changes by 5%, the collector current will not change by a factor of 4.65. It will change by a much lesser amount. So that's what we would like to prove. And we have to go through some steps of calculations and analysis to prove that, and then we'll see how that comes about. All right, so let's just prove one point which will greatly help us, and I will call that observation. And I will take this circuit in isolation without the biasing components yet and perform a simple experiment on it. So here's a simple common emitter stage with degeneration. We have a resistor here, and we come along and change the base voltage by a small amount, delta V. So let's say the base was sitting at some voltage, right? You had maybe 0.8 volts, 0.9 volts, 1 volt or something. And I changed it by some amount, a few millivolts. And the only question I want to answer right now is, what happens to the voltage at this point? Does this voltage go up, go down, or remain constant? That's what we would like to know. Okay, well, we can pick one of them and proceed and see if the result agrees with our assumptions. If not, then that assumption is incorrect. All right, so let's say delta V raises the base voltage like so, and let's assume that the emitter voltage doesn't change at all. Okay, so would that work? Does that make sense? All right, so here's what we're saying. The base voltage goes up, the emitter voltage does not change. All right, what happens to the collector current? The base voltage goes up, the emitter doesn't change, so the base emitter voltage increases, which means IC must increase. So we are saying that IC increases. If IC increases, the emitter current also increases. They're approximately equal. So the current through this resistor increases. If the current through the resistor increases, what happens to the voltage on it? The voltage must increase. So this point has to go up. So that contradicts our assumption that this voltage is constant. So we can quickly see that the right answer is that when the base voltage goes up, the emitter voltage also goes up. Now, does it go up by the same amount or not? Well, we don't know. But all we know is that if the base voltage goes up, the emitter voltage has to go up by some amount. It cannot stay constant, and it cannot go down. Okay, so that's good to know. In a common emitter stage with degeneration, if the base voltage goes up, the emitter voltage has to go up. And that's, of course, in contrast to when we have no degeneration. We have no degeneration and the emitter is connected to ground. When the base goes up, of course, the emitter doesn't go up. The emitter is tied to ground. But here, the emitter voltage has to go up. Okay, so let's remember this observation, and now we are ready to understand why this circuit is better than this circuit in terms of supply variations. We are hoping that when this supply goes up by 5% and this base goes up by 5%, the collector current doesn't blow up by a factor of 4.65. So is that something that we can predict? Well, to some extent, what we can see is the following. If the supply voltage goes up by 5%, and the base voltage goes up by 5%, because it's still given by this type of equation, well, the base goes up by 5%, but the emitter voltage is not constant. The emitter voltage also goes up. So if the base goes up and the emitter goes up, so going back to the example, if the base goes up by 40 millivolts, and the emitter goes up by some amount, we don't know how much, what we can say is that the base emitter voltage does not increase by 40 millivolts. So I repeat, the base voltage goes up by 40 millivolts. The emitter voltage also goes up. That means that the base emitter voltage does not go up by 40 millivolts. It goes up by less. Therefore, the change in the collector current is less than what we had here. So that is the beauty of emitter degeneration in reducing the sensitivity to supply variations. All right, so our time is up. Next time we will quantify all of these observations and see exactly how much improvement we can get, how much improvement we can get in the sensitivity as a result of a certain amount of degeneration. I will see you next time.